The classical concepts used to describe electrical conductivity in materials can also be used to describe the thermal conductivity of materials. Imagine we have our material that contains atoms that can vibrate and electrons that are mobile, placed in a temperature gradient between hot and cold that will allow heat to flow through it. Thermal conduction in a material involves the transfer of energy from the hot side to the cold side, either by these vibrating atoms or the transporting electrons. The vibrating atoms on the hot end move slightly faster than those of the cold end. Also, the electrons that can transport also move slightly faster at the hot end rather than the cold end. Thus, when the atoms or electrons collide with one another, they generally move energy from the hot side to the cold side. This transfer of energy from the hot side to the cold side is known as the thermal conduction. The flow of heat from hot to cold can be considered like charge flowing through a conductor. The amount of heat that flows through a conductor should be proportional to the cross-sectional area as well as the temperature gradient pushing the heat through the material. Mathematically, the rate of heat flow, or the amount of heat being transported per unit time, is equal to the cross-sectional area times the temperature gradient, and a constant we call the thermal conductivity. The negative sign here is needed to make sure that the conductivity flows down the temperature gradient from hot to cold. This relationship for thermal conduction in a solid is known as Fourier's law, which states that the rate of heat flow is equal to the thermal conductivity times cross-sectional area over length L times the temperature difference. This is exactly analogous to Ohm's law for electrical conduction, where the heat flow is analogous to the electrical current, the temperature drop is analogous to the voltage drop, and the thermal conductivity is analogous to the electrical conductivity. The thermal conductivity of many metals is plotted here along with their electrical conductivity, and one can see there is a strong trend of increasing thermal conductivity with increasing electrical conductivity. This relationship, which can be written as the thermal conductivity divided by the electrical conductivity equals temperature times a constant, is known as the Wiedemann-Franz law. This strong relationship here for metals suggests that the same carriers that carry the electrical conductivity are also carrying heat, providing for a very high thermal conductivity. The Wiedemann-Franz law is often written as thermal conductivity kappa divided by electrical conductivity sigma times absolute temperature T equals a constant, where this constant is known as the Lorentz number. The Wiedemann-Franz law can be justified by considering that electrons carry not only charges for the electricity, but also energy to transport heat. We saw that electrons that move randomly have a net drift velocity when placed in an electric field, providing a net current flux, which we write here as J sub E for electrical. Similarly, we can describe the heat flux of these electrons, J sub Q, as the density of electrons times the excess energy that they carry and their drift velocity for transporting energy. Now, since the same electrons are carrying both charge and energy, they should have the same mean free path and tau, as well as the same mass and mobility and carrier concentration for both mechanisms. The mobility mu tells us how much drift velocity we should get from an electric field. Converting to force, we see that the drift velocity is mu over E times the force. Now, if instead of electric force we use the force due to the temperature gradient, we should be able to figure out how much drift velocity we get from the temperature gradient. Because a force arises from a gradient in energy, we can show that the thermal force arises from the gradient in thermal or kinetic energy. Using the chain rule, we change the gradient in thermal energy into the temperature derivative of energy times the temperature gradient. Now we recognize that the derivative of thermal energy with respect to temperature is the heat capacity. Next, we solve Fourier's law for thermal conductivity, giving us thermal conductivity kappa is the heat flux J divided by the temperature gradient. We then put in our equation for the heat flux and then substitute for drift velocity our generalized mobility and force. Then for force, we want to use our thermal force, where we see that the temperature gradient has canceled out on top and bottom now. With N times mu up here, we can now see how electrical conductivity is going to be related to thermal conductivity. For the Wiedemann-Franz law, we are interested in kappa over sigma, thermal conductivity divided by the electrical conductivity. So we use, for the thermal conductivity, the expression we derived here, and then for the electrical conductivity, the well-known Ne mu. Next, we see that the N in mu will divide out on top and bottom, which leaves us with only the average energy of the electron, the heat capacity, and the electric charge. Now, for a classical gas, we have the thermal energy is roughly proportional to the temperature, kBT. And also taking the derivative of this thermal energy with respect to temperature gives us the heat capacity is simply the Boltzmann constant. And so now finally we can plug these two expressions in for our expression for kappa over sigma, giving us the Wiedemann-Franz law, kappa over sigma is proportional to kb over E squared times temperature. To summarize, the Wiedemann-Franz law comes about because our electrons carry both energy as well as electricity. In addition, we have used the principle that the mobility of these same electrons should be the same for an electric force as it is for a thermal force. A similar principle was used by Einstein in deriving that the diffusion coefficient should be related to the mobility by considering the diffusion force of the electron.